So let's give you this to look at for the next couple minutes. Just kind of absorb it, go through it. I don't know if you want to move over because I'll be probably, yeah. Shear force?
Like, is that like an internal force? Like,
it's an internal force. I'll draw a little diagram once everybody's kind of, when I start doing this. I keep on getting in your way, so I apologize. So, yeah, that's 3. There, is that better? Before you sit down, man, can you grab one of these surveys up front and just have it back to me by the end of this session, please? Thank you. Oh no, it was just, it didn't print well. It was just blurry on the paper. Thanks, Sam.
Are you trying to zoom in on the document?
No, I wasn't.
Oh.
All right. Has everybody had enough time to digest the problem? Trying to see what direction you guys want to take it. All right. So what's the first step we should do here? Reactions, okay. First step in any problem, we have to solve for the reactions, right? All right, so where are we going to start from that? Or where are we going to start with that? I'm sorry?
Forces on the Y.
Can you do forces on the Y? A moment about A probably would be a little bit better. All right, so at least that's the way I went. Start with a moment about A, and then you can go to your forces on the Y. You need both either way. And again, I hope I'm not blocking anybody's view. All right, so we're going to do sum of moments. And A equals 0. All right, so looking through this first term, where did that come from? The first term right here. Okay. Okay. So yeah, I took the base times height of the concentrated load, got into a single force, put it down the center. So I took this, did base times height, so it's going to be just base times height, which is going to equal 8 meters times 40 kilonewton meters. Now if I would leave the meters there, so we're looking for a concentrated force, right? So if we're taking it from a unit perspective, all we have to do is just cancel the meters, and now we're left with a single force after we multiply the 8 by the 40. And that's going to be the concentrated load for a rectangle is down the center, right? So that's where the concentrated load would be. And that would be 4 meters from the left. Does that make sense to everybody? And I don't know if you guys want to move because I know I'm blocking your view. Yeah, so. All right, so this next term, where did that come from? The by times 8 meters.
By is counterclockwise at 8, and it's 8 meters.
Okay. So yeah, we got the by at 8 meters is right there. Got our little reaction force right there. We're just going to put a happy little reaction force right there, right? And then move on. So, and that's our unknown. That's what we're trying to solve for. And that's why we're taking the moment about A, right? Because what does taking the moment about A do? What does it do to this reaction force? 0. Because what? Because the radius or the distance is 0. Because we're always concerned with the perpendicular distance. And then this last term, what's this?
20 kilonewtons times the full distance of the bar, which is 1 meter.
Okay. So, and then the full distance of the bar. And this last term, right there. I'm sorry?
150 concentrated moment.
Yes. And why do we have negatives on these two? Clockwise. All right. So you do all your math, and By is going to equal 206.25 kilonewtons. Anybody has any issues with that? No? All right. And then from there, we can move on to our sum of forces in the Y. Now, the only reason I like doing the sum of forces in the Y second is because you're still going to have 2 unknowns initially. So if you just do your moment first, then you just go right into the sum of forces of Y with 1 unknown. Everybody see that? Anybody have any issues? Anybody have any questions about how I set this up? Everybody good? Okay, so AY and BY are now solved. Now we can check it. We can plug it back into the equations, make sure it equals 0, correct? And that's a quick check. But if you're running out of time and you just got to say screw it and move on. All right, so now what's our next step? So all right, so we got to draw shear and moment diagrams, right? Now, how many different methods do we have? 2, which are? Okay, integrals and sections. Not everybody gets taught integrals, so I will not be going through that method. I'll be going through the method of sections here. If you want, you can ask me after class about the method of integrals for any of this stuff, and I can try to show you quickly. But the key to the integrals is you got to practice, because you have to solve for C. And initially, if you're starting out on the shear and moment diagram, C is easy because C is 0. But if you do it midway, you got to solve for the C. So I can show you how to do that afterwards if you guys want me to show you, but I can't do it during the presentation, I'm sorry. So we're going to go, and we're going to start out with making cuts along the beam. So where should our first cut be? All right, so somewhere in between A and B. Does it matter? It's concentrated load, but does it matter where we cut it? No, not really. All right. All right, does anybody have any issues with the way I set that up? I am not an artist. Nobody tells you you have to be an artist when you start engineering, so I apologize. Does this make sense to everybody? So we made our first cut down the middle, right about there, and we broke it in half. And then to answer your question from earlier, the shear is an internal force, because if we make a cut left and right, the shears always have to be opposite of each other, right? Because we're in equilibrium. So it's always going to be the internal force that reacts on the body. All right, so looking over here, what's our normal force going to be? 0, because we don't have anything in the x. All right. Now we have to solve for shear, and we have to solve for a moment, right? All right, so let's just start going through that. Do you guys want me to give you a couple minutes to try to do it, or do you want me to just go right through it? It's up to you. No? All right, let's go right through it. All right. Everybody kind of take a look at that. Does everybody agree with what I did? Does anybody have any issues or questions?
So we can just set x whatever we want.
Well, your reason you make your cut is because you're pretty much saying that it's an x variable throughout. So you have to make an equation for the line of the shear graph. So if you're looking at it, it's a way of conceptualizing it. You can break it up into sections, right? You can either make the cut here, but you realize that your equation for this entire section is going to be the same. So you're making an equation for every change in the beam. Does that make sense? Yeah, so yeah, your line's going to be different here than it is here. So every time there's an additional outside force acting on that beam, you're going to have a different equation for your line. That's why you go through these. You can calculate the shear at any point on that beam with that equation of the line. Any questions? No? All right. All right, from here we're going to go on to moments. And where are we taking our moment? What are we solving for? We're solving for this. We're solving for this moment right here, right? So, yeah. Everybody following? Yeah. Because if I took it on the other end, the other moment would cancel out. Everybody following? Shear moments really aren't that hard as long as you realize that you're taking away the distance and just leaving it as a variable. And then it just becomes algebra. And that's all shear moment diagrams are going to do. That's the most difficult part. All right?
So, if the shear force is variable, like it changes based on where you make the cut, why did we pick 133.75 to be the shear?
It's just halfway through it. It was just easy to calculate. You're going to start doing intuition-based stuff from here on out in the engineering classes. So just try to make it easier on yourself when you choose where to do certain things.
Okay.
That's all. Because it really doesn't matter where we cut it. It's just the ease of the math of where we cut it. Does that make sense?
It makes sense.
Okay. Because yeah, I mean, you can make this as difficult as you want or as easy as you want. But no matter what, where you make the cut up here, that line is going to be consistent. And the equational line is going to be the same. So it really doesn't matter where you make the cut. All right, so we have beginning and we have an end. So now we're going to move on to a second cut. And where's that cut going to be from and to? So it's going to be from here to here, right? Because from here to here, we don't have anything happening. So the line does not change whatsoever. So we have another section that we have to do. And that's actually how you find out that how many cuts there's going to be, by the external forces acting on the system. So because there's only one line here and one line here, you have two cuts. So I go over here. Does that make sense to everybody? Anybody have any issues with what I did? Because we're doing method sections. If you were focused on integrals, you would only have to do that section. So integrals, you're only concerned with that line at that point, but when you do sections, you have to incorporate everything else. So you could have taken the cut from the right too, but I'm just going to be consistent and just make the cuts from the left. Any other questions? All right. Then we're going to move on to our sum of forces in the y, and we're going to do our sum of moments because our n, the normal force is going to equal 0 because of the lack of forces in the x direction. All right. Does that make sense? Anybody have any issues with that? Now, just looking at this, does this conceptually make sense? to have just 20 kilonewtons shear force. Yeah, and there's no distributed load either, right? So it's just going to be a straight line. So just looking back at the diagram, we don't have anything in between here, so we're just looking for a straight line. Then we're going to move on to moments. All right, does that make sense to everybody? Anybody have any issues with that? Yeah, so this comes back to the line. So where does the line change and where's the line consistent? Yeah, so there's no change to that line equation of that line in there. So that equation is specifically for that section of the beam. Make sense? All right. And then if you want to touch on integrals a little bit, what do you notice about those two equations? Yeah. If you just integrated this equation, you would get this equation. And you wouldn't have to do a sum of moments. But the second part? It's the moment for the entire beam. So A is 206, right? So we have 206 minus 8, because that's that. Yeah, so it's the entire beam. But yes, but it gets a little hairy over here when you start integrating the shear of 20, because now you have to solve for a C. So that's why it gets a little difficult with the integrals. You can do a quick one over here without really practicing it very much. You just integrate the one equation. But when you're actually mid-beam and you have to integrate the equation, it gets a little hairy. So you really have to practice it if you want to use method of integrals. All right. Now looking at this first equation, actually let's just start doing the shear moment diagrams. All right. All right, so on the shear diagram, where are we going to start out? Where are we starting on the shear diagram? So we have a reaction force all the way on A, right? So technically we start out always at 0. However, this is going to shoot up, and we're going to be at 133.75. Does everybody understand why that is? All right. So any kind of point load is automatically going to be a vertical load that's on your shear diagram. So you just go up that amount or down that amount. And then from there, where's our next point? Negative 186.25. And that's at where? All right, is that 8 meters? So we're going to make a little dotted line right there. So looking at this, you automatically know your beginning and end right here. So you can automatically know where your line is going to change on this graph. So all you have to do is mark it down, because this is going to be your x distance. And then what kind of a line is this going to be? It's going to be a linear line. All right, where are we going from here? All right, we're going to go up by 206 because of the reaction force, correct? All right, we're going to be left right there, and it's going to be 20. And then from here? Constant. And what do shear and moment diagrams always do? End at 0. That's right. If it does not end at 0, you have screwed up. You have to go back and redo everything. All right. Let's work on the moment. All right. So where are we starting out on the moment graph? 0. Why do we always start out at 0 on the moment graph? What is the equation for a moment? What's our distance at 0? We always start at 0, unless there is a concentrated moment. All right, so what do we know about this line? What do we know about it? Just looking at the equation. Think back to calculus. It's a parabola, negative, so it's going to be a concave down parabola. Just by looking at the equation, you already know the generic shape of it. And then we also know where it ends, right? At negative 210. And that happens right at the same spot as our shear. So if you draw your shear and moment diagrams vertical of each other, you can just pretty much translate what you see to shear and moment at the same time. How are you going to figure out what the peak, where the peak is? You get, sorry, I got.
Set it equal to 0.
Which?
The equation equal to 0.
So we're saying the shear equation equal to 0, right? Because what do we need to find at the shear equation? Yeah, we need the distance, right? So right there, it crosses the axis at 0, so that's an easy solve. So our max moment does anybody want me to write out that equation about how I solve that? All right, here. So you take your shear equation, right? So this is our shear equation. And we have to find out the x value for when shear is 0. So we just set shear equal to 0. So 0 equals 133.75 minus 40x, and then solve for x. All right? And that's going to be where the shear crosses the x-axis, and that's going to be the point of a max moment for that line. All right? And I'm sorry if this is not to scale. All right. Oh, sorry. So does everybody see kind of what I did there? If you draw them vertically, you can just pretty much draw dashed lines. It does make it look pretty, but it also helps you out a lot trying to line everything up and makes a little bit more sense when you're actually needing to do calculations in future courses. How many mechanicals and aerospace do I have in here? You will do all of this again. So remember, this will come back. If you do not get good at this, this will haunt you in the future.
Where will it come back? Like thermo?
Solid mechanics and machine design. Because you do internal components again. Because you're going to do shafts, gears, all this other stuff where you need the internal stresses on the material. All right. So now we got the next sectional line right here, right? And we have this equation. So what is that equation? What's that line going to look like? Okay, so it's going to be increasing. Why is it? So it's a positive slope, right? Why? Think back to calculus. Just look at the equation. Because x is positive, right? There's no negative in front of the 20. So we're going to have a positive slope. So that's going to be an upward slope. But as we calculated up here, it only takes us to negative 150. How do we get back to 0? The concentrated load. All right? And just thinking about it from a mathematical perspective, you integrate a negative slope line, linear line, you get a concave down parabola. You integrate a positive horizontal line, you get a positive slope linear line. Which one? This one?
Yep.
Right there.
Why is it minus 370?
So it's easier to explain if we did the integrals part, but that's pretty much after you solve this equation, that's the constant that you're left over with. So if you were to integrate this, you'd have 20x plus c, and then you would, when you solve for c, you would get 320 or 370. Sorry.
But why is it like at the cross in the middle? Is it negative 210 for the parabola on the left side? Does it make sense? Why are you starting at negative 210 for the parabola, but then that one's supposed to start at negative 370?
So this starts at 8, right? So that starts at 8, not 0. So if you put 0 in there, yeah, we would start at negative 370, but we don't. So over here, when we finished at 8, the moment stopped at negative 210. All right? Does that make sense? So we stopped here, but then we needed some other kind of a constant. So that's our constant. So when you solve the actual total moment equation, you're going to be left with this constant times 20x, or subtracted from 20x. All right?
You start from the 210.
Yeah, and you start from 210. So that's how these two equations link. So at 8 meters, both of them will equal 210. Does that make sense? Does everybody have any questions about that? No? Is everybody okay with this? All right. So I got one more shear moment for you guys to go through. Again, I'll give you 5 minutes just to kind of look at it and try to start working it out in your head and see where it's going to go, okay? All right. So, do we have anything in the x? No, so we don't have to worry about it at all. What's the first thing we're going to do?
React.
All right, so let's solve for the reactions. Again, we're going to need two. Which two equations are we going to need to solve for the reactions? Okay. So for my moment, anybody have any issues with that?
Why is the distance 4 when you're doing distributed?
So this is 6 meters, right?
Yeah.
Where's the force resultant for a triangle? It's going to be 2/3 from the left or 1/3 from the right. So, or 1/3 from the highest end or 2/3 from the lowest end. So that's where the force resultant is going to lie. Any other questions? No? All right, so yeah, our force resultant is going to be right about there. And that's going to be at 4 meters. Everybody good with that? All right. We're going to do some forces y now. Everybody agree with that? No issues? All right. Now we can check it quickly to double check, but I'm not going to do that. All right, so where are we going to make our first cut? Distributed load. Is anybody comfortable in here doing the cuts on the triangle? So this is going to be a learning experience. Let's do this. Does everybody see what I did?
Why did you get X squared?
So going over here, base times height. So when I made the cut, so 1/2 base times height is the area of a triangle. Anybody else? What's up?
The 2X.
The 2x, so shear. So you have 12 kilonewtons,
Right.
but I'm making a little bit of a ratio so that if I'm making the cut a little bit early, so if I make the cut at 6, so I'm assuming this is halfway. So halfway through the triangle, you're assuming it's the height of 6 instead of the full 12. So you make the ratio out of it, and then you put a distance on it.
Why is it 1/2 x? Why are we wanting?
Because the area of a triangle is 1/2 base times height. So your base is your x distance, and your height is the variable 2x. Does that make sense?
Yeah.
All right. No more questions? All right. So from there, this is the hardest part right here, is trying to develop these. So practice these. If you find a couple more problems, I don't know how many more review sessions there are for statics. But I'm sure there's going to be more triangle loads on there. Try to practice a little bit more of these. These can be confusing, I know. So it just really takes a lot of practice to get used to the triangle, especially setting it up through method dissections. All right, so now we're moving on to sum of forces in the y. Everybody good? Just simple sum of forces equation. Bless you. And now we know we're going to have to be concerned with a max moment, right? So we might as well solve for when shear equals 0, at what distance that is. At v equals 0. So max equals 3. What's up? Oh, sorry. Apologize. So this is going to be the distance where the x crosses the, or the shear crosses the x-axis at 0. And this is going to be the distance of your max moment for this equation. Questions? All right, moving on to the moment. So thinking about it, if we're doing like integrals and stuff like that, what do you expect the moment equation to be if we integrate this? It's going to be cubic.
9x minus x cubed over 3.
Yep. Yeah. It's easier when it starts at 0 because then c is not there. But when we get over to here and you try to do it, it gets a little hairy when you try to have to solve for c. It's easy, but I'm not going to go through that right now. All right, now we're going to move on to our moment. Questions? This one, it makes a little more sense just to integrate it. It gets a little confusing when you do sections, especially with a triangle, because you're adding a bunch of stuff in there. But if you're comfortable with integrating, I just totally recommend to integrate it if you start at 0.
Why did you do x over 3?
I'm sorry?
Why did you do x over 3?
Down here.
No, up in the first, like when you roll forward, yeah.
1/3. From right. Yeah. Questions? And again, if you just integrated this equation up here, you would have been just left with that. All right. I mean, I got it. All right, so we figured out all the points with the triangle, and now we're moving on. So we only needed 2 cuts, right? Because the line only changes twice. So now we're going from B to C. And what kind of a line are we going to have? Yeah, we're going to just have a straight horizontal line. All right, so our second cut. Anybody have any issues with that free body? Nope. All right. All right, so now we're just going to go on to our sum of forced equations and solve for the y and the moment. Anybody have any issues with that? Any question on where the terms came from? All right. Then we're going to move on to our sum of moments. Anybody have any questions about that? So again, If you looked at it from an integration perspective, if you just integrated that, you'd be left with a 6x, right? And then you would have to solve for a c. But here we had to do the method of sections, which we had to leave the variables in there. All right. Any questions?
Is that 34? 6x minus 34? 54, what is that?
Oh, 54, sorry. Yeah. All right, and again, you notice without a concentrated moment or anything like that, where we leave off here at the moment of negative 18, we start at the moment of negative 18. So that's a little bit of a consistency. You can test your equations that way to make sure they start at the right spot. All right? Move on to the diagrams. This should be pretty easy since we have all the information now. All right, for our shear, where are we starting off? All right. Yeah, so we're going 0 up to 9. All right, so looking at it, at the equation, so it's negative, so it's going to be some kind of concave down, right? Right? All right. And then where we cross the x-axis is at 3. So let's just say that's 3. Something like that. All right. And then we leave off at negative 27. Is everybody following? Any issues?
And that's supposed to be 9 minus x squared, right?
9 minus x squared, yeah. Yeah, since the x is negative, we're going to have a concave down. All right. Then always fill it in. If not for you, in order to go for that partial credit, in case you can't read your work. All right, so now we're starting at negative 27. Where are we going? So we're going to go straight up to positive 6. Is everybody following that? We're doing that because of the reaction force of By. And then what happens to the line in this equation? So it stays constant, right? So we're going to have a horizontal line. Right? And then what happens at the very end? So since we have that point load at the end with negative 6, we go right back to 0. And 0 is the happy place, right? And that means you did everything right. You would hope. It could be a happy accident, but we're going to go with you guys got it right. All right, so now we're trying to oh, sorry. This shouldn't be shaded in. That should be shaded in. Sorry.
Which side should be shaded?
Yeah, this side. Sorry.
The side between the x-axis.
Yeah, it should be this side right here, not this. Yeah. Sorry. Just like you, I am studying for my own finals as well. All right, so now moments. Do we have any kind of concentrated moment at A? No, we do not, so we start at 0. All right, and we know our max moment is at 18 because we calculated that out down here. So we put 18 up there, and then we know we end at negative 18 down here. So even if you didn't know how the line was going to look, by plotting those 2 points, you can draw it, because it's going to remain consistent. All right? Does that make sense? Does anybody have any issues with that? So even though you might not be confident with how you're going to draw your moment line, if it's concave up, concave down, or whatever like that, if you know what the max is, you know what the min is, you know where to start, you can draw it. All right? Then we're going to shade these in. This is going to be our max. This is going to be our min. All right. And then from here, what are we doing here?
Going from negative 18 and 6 to 0 at x equals minus, which makes the linear graph.
Okay, so a linear positive slope line. Back to 0. Does that make sense? Yeah, if you guys just review a little bit of your calculus about how the dynamics of lines and integration, it really makes shear moment diagrams a lot easier. Any questions?
What's the peak value of the moment again in the diagram?
It's 18. No questions? All right. Do you guys want to do another shear moment, or do you want to move on to centroids? Centroids? All right, I'll give you guys a couple minutes just to look at this over and see if you can start working it out in your head, and then we'll start going over it. All right, so who's ready for some calculus? All right, so where are we going? Left, right, up, down? How are we gonna scan? All right. All right. I forgot how much. All right, so let's get the formula out and start going through it. So we're looking for x bar. So it's pretty much a plug and chug formula as long as you set up the equation correctly. Look it over for a second. Make sure that I didn't do anything wrong, please. All right.
The coordinates that you did up top there, you had x and you had y and 2. Are you just assuming that you're cutting it in half with y?
Yeah.
So at the end when you find y, then you're just going to put over 2.
Oh yeah. Well, the y over 2 is going to be integrated into the actual initial stuff. Or the initial equation. Sorry. Everybody go with that? What's up? Oh, sorry. Again, these are generally easy. You just have to make sure that you set it up right. You scan it from the way you want to. left to right in this case, because that way you don't have to worry about cutting stuff away. All right, so let's move on to Y-bar. And remember, for dA, we have y dx. All right. And this did take me a while to solve for this, so it's not going to take you guys 5 minutes by any means. It did take me a good 15 minutes to figure it out. So don't worry if you're lagging behind or I'm just going through this too quickly. So here's our Y-bar. Any questions? Thank you, man.
So, how did you know to put y over 2? Because the way I learned it is we'd have to solve for x using the equation and then do y times.
I took an arbitrary y over 2 by halfway.
X, y over 2. So, can you explain why you did that and the reasoning behind that?
No, I just, that's the way I learned it, is I just take a halfway point and just say I cut it in half.
Is there another way to do that?
Why the top line there?
Well, you can solve for y and solve for x in here, so you can resolve these.
That's the way I
Yeah, which you can do, but I just halved it. but it ends up being the same answer. That's all.
So if we don't already put in the y over 2, we would just solve it. So you would get the 3/5h, and then that's when you plug it.
Yeah. By all means, please review this. If you have any issues, please come to me. This is just the way I learned it. And I am in the same boat as you guys, so every day's still a learning process. But yeah, for Professor Ortiz, I know you guys are not going to have one of these. This is just good to know. No, he said that in class. You guys aren't going to have one of these. But I know Professor Zorn likes to give these. So just be prepared for it. And again, if you're comfortable with this, all it really is a plug and chug equation as long as you get it set up correctly.
What is this? This is Centroid stuff?
Yeah, this is Centroid stuff. He's going to have you do the regular stuff. He's going to give you an object with distances. Yeah. No.
That's just basic calculus, I mean calculus, that's just. But are ours gonna be in 2 and 3D, or is only gonna
He might give you a 3D.
be surprised with
All right, now let's go on to more of a simple centroid with just some numbers. Let's give you a minute to look over that quickly. These go pretty quick as long as you know what you're doing. They're just a little tedious.
Similar to the other one, except you just use piecewise function.
Yeah, since you're given distances, it's a lot easier. So you don't have to integrate anything, so you can use common shapes. And then just locate the common shape centroids, sum them up. All right, so moving along, I'd like to get it through. We only have about 30 minutes left, so I'd like to get through at least 2 more problems. All right, so how many shapes do we have here? 2. 2 is the most efficient way. One there. Right? And one there. Anybody have any issues with that? No? All right. Centroids for each, right in the middle, they're rectangles. That's pretty easy. So we're looking for y bar, right? So what's the equation we use for y bar? Right? Sum of y squiggly times area over the sum of area. Yeah, summation of y, sorry. I've been trying to keep the handwriting neat, so I apologize. All right, so now we're going to do it in the tables. Does Professor Zorn do the tables with all these? All right, so sections. We're going to have 1 and 2. Area is going to be millimeters squared. Y bar, millimeters. All right, so section 1, we're labeling as top. Section 2, we're labeling as the bottom. All right, So did anybody actually do the calculations on the top and bottom? No? All right. Well, let me tell you what it is. So the area of the first one is going to be 72,000 millimeters squared, and the area bottom one is going to be 28,800 millimeters squared. And then we're going to have the sums down here. And this is going to be the sum of the area. All right. Does anybody have any issues with what I did there? Area is easy. Base times height.
So you did the 120 times.
Yes. So I took this first one, 120, times the sum of the total measurement on the bottom. Sorry, I'm skipping some of the formulas and stuff now. I want to get more to the previous things for you guys that are doing the cumulatives. All right, so our y bar. What are we doing with our y bar? So according to this picture, where's our datum? Yeah, where's the y bar for the first one? Or for, sorry, this one up here.
Half of the 120, but
300, yes, correct. Does everybody understand how we got that? No? All right. Would you like to explain it?
when you're doing the Y bar and you have it above the second one, you have to add the distance from it below and then do half of the Y, which is 120. You do 240 plus the 60 to get your actual location, if that makes sense.
You're
Yeah.
just trying to find the y coordinate of the centroid to the
Yeah.
to the figure you're trying to do.
So from here, he did 240 plus half of that, and that was the centroid of that. Because we're looking for the total in y, so we need both. All right, so using that, what's the second one? What's the centroid for the second part? So for this one right here.
Oh, wait, no. 120. Yeah, 120.
Okay, that's right. Do you see that? All right. Yeah. So yeah, it's from this baseline. So a distance from this baseline up. All right. All right, and then as you see in the nice chart, y squiggly times area. So since we kept it in millimeters, let's have a big long number. Oh, one second. There you go. And then the sum. Anybody have any issues with that? This is straightforward, just y squiggly times the area. That's on the chart already. All right, now what do we do with these two numbers? All right, so you just throw them right in, these two numbers, you just throw them right into that equation. So your y bar is going to equal 248.57 millimeters. All right. Now logically, does that make sense? Well, this is the y bar coordinate, right? So does this make sense that it's up here above the 240 and outside, right? Because this is greater. So that's just a quick check and just making sure that your math is sound. Just like, okay, this is a bigger piece, more mass, it should be up a little higher.
So if you were to do the x, would they be the same number?
Since they're in the center, yeah. That's why they never ask you to do the x. Feel free, by all means, but you'll waste time on the test. All right, everybody good with this? That's it. They just asked you for the y bar. Yeah, so I mean, this is a very, very short and sweet one. This is something Ortiz would give you. So it looks complicated, but it's not. You guys want to do an inertia, or do you want to go back to previous things? All right. Look at that for a minute. It's good. That's the reaction I was going for. So yeah, just look at this for a couple minutes, try to figure out how you're going to tackle this, and then we'll start going over this. All right, so how are we going to start this off? Deciding which shapes go where. All right. So what shapes do you see?
Rectangles and then weird hourglass with the thing.
All right. So we got these and the overall thing. So in order to get the total shape, does that make sense? All right, so moment of inertia of the rectangle. Does that make sense to everybody? So this is our eye of the rectangle. And where do we get this equation? Right here? Always in the book. You can memorize it if you want, but most likely you'll be given the tables.
Question. To get the height, do you just do 200 times sine 45? Or, I'm trying to figure out how you got that.
Yeah, so these are just triangles.
So you just do that triangle and then the one underneath it, so you have to fold?
Yeah. Oh shit. No, I did this. We also need 4 rectangles. Or 4 triangles. Okay. Yeah, all right. All right, so this is going to be for the arcs. And again, these are in your tables. Yeah, sorry. Right. All right. Does that make sense? So now we're doing the arcs. Right there. Yeah, this formula will be given. That's in there. Yeah, it's in your it's in your status book.
Why is the AC y squared over 0?
Because we're just concerned about the moment of inertia. Because the inertia itself, like if you look in any other textbook, you never ever use it additional with area.
What is
So you're just using.
what does that do? Like the ABY squared?
I can get back with you on that. I don't know exactly. So I'm not going to lie to you. No, in any other class, you're always going to see the moment of inertia like this. You're never going to see it with additional area on the end of it.
It's probably if it's not rotating about the centroid, right? Then you'd have to use that.
No, because even if you didn't, there's already moment of inertia formulas for outside of the centroid.
You
So.
can't use degrees for the theta.
I'm sorry?
You can't use degrees for the theta. Like 45 degrees, so it's pi over 4.
No, because I mean, if you're going to use it like this, you can't.
Okay.
Because if you times it by sine, you're going to be left in radians, right? So the degrees are not going to be there anyways. So if you just leave it in the numerical format, you'll be better off.
Okay.
Make sense?
For the moment of inertia for that sector, that's only one of those 45-degree sectors, right?
Yeah, so we have to times by 4.
Okay.
Or, sorry, this is times by 2. So with this, I'm doing this.
Then why is the theta pi over 4? Isn't that 45 degrees?
It was, remember 2 theta? So
but the theta over.
yeah, if you put if you put pi over 4 into there, times it by 2, it's pi over 2.
Right.
That's just the formula.
Yep,
There.
theta, it's
Yeah, theta pi over 4 is 45 degrees.
Right.
Yeah,
So
pi over 2 is 2 times theta.
right. So we're doing that whole 90-degree sector,
Yeah.
even though theta is only 45 degrees.
Yeah, so we're adding them up.
Okay.
Yeah.
The way the formula gives it to you, it gives it to you from the axis to the end of the ray. It's not the whole section.
Okay.
Yeah, sorry, I don't have the book with me.
So you just multiply it by 2 to get that.
Well, that's what the formula says.
Yeah. So this is straight formula. So theta will be right here in the formula, but this is the formula to theta right here. So that's straight out of the book.
Just subtract it.
Yeah, and then it's just subtracting out. All right, I got 10 minutes left. If you want, I can finish this up, or I can do a sections quickly. You guys want me to do a sections quickly? I'll post the solutions of this online after this, so you guys will have it. Is that cool with everybody? Sorry, I want to make sure that I cover some of the previous stuff for you guys.
You just subtract the moment of inertia of the rectangle, or the moment of inertia of the sector from the moment of inertia of the rectangle, right?
Correct. Yeah, it's
Just the last step.
yeah, it's just like centroids, where either you have a whole block and you're cutting pieces away, so or you're just kind of adding pieces to it. So I mean, it's just like if you ever did CAD software, if you've ever worked with CAD before, you draw a gigantic rectangle and then you start cutting sections away to get the shape you want. So it's kind of like that. Yep. And I'm sorry if I'm rushing, man. I just want to get to, or guys, I would just want to get to help out some of the other people that are doing a cumulative. All right, let's do sections. So just look at that for a minute.
Glad I don't have to do that anymore.
This one's actually easy. So as long as you get the zero force members right. Two I joints. Here's I and J. Sorry. It's a blurry print. Sorry, man. All right, so looking at this, how many zero force members do we have? Anybody else? All right, we have 6. Yeah, so BC, BA, CD, right, DE, HI, and IG. Those are our zero force members. So, as you can tell, this simplifies the problem a lot. As long as you have the intuition to see the zero force members initially, you're good to go. And just remember the simple rules like the perpendicular members with no external force.
ED is a zero force member?
Yes. So there's a force down here. IJ. IG. Yeah. This, I struggle with the zero force members sometimes, even now. So it's really intuition based, whether you can tell right off the bat, if not, whether they are or not. If not, you can start doing joints and sections, and then they'll obviously pop out as soon as you start doing your analysis. All right. All right, so after we identify the zero force members, we're going to move on to support reactions. So best way to start is with a moment. Where we would want to take a moment about? A. Why? Because it cancels both forces out. All right, so, and then we have nothing in the x, so ax equals 0. And there are some forces y. Yeah, it's pretty much, it's assumed there's no external forces in the x direction. All right, and then we're left with our AY equal to 4.5. And what does the question ask? Determine IC and CG. So we're looking for CG and IC. All right, so what's the best way to do that? Where should we start? Could we section it off? Or is there too many unknowns? Could you do sections, or do you have to do joints? I'm sorry? Oh, sorry. I apologize. Can we do sections, or do we have to do joints? We can do sections. How many unknowns? Or where would we cut it? Just horizontally, like this? We can cut it horizontally like that. And how many unknowns do we have? We would have 3 unknowns, and we have 3 equations to solve, right? But if you want to make it easier on yourself, you can do a joint, and then solve for this member, and then come up here and then do the section. So you can do the combination of the 2, just one, or the other. In the end, it really doesn't matter as long as you get it done. So it's just a little less algebra if you just do a little bit of a joint right here, figure out the initial force. That way you can carry it up here and you only have 2 unknowns to worry about. All right? All right, so we're out of time right now. So I will post these on the Study Union website with the solutions. And I apologize I didn't get through everything. I hope it was helpful for you guys. If you have any other questions, I'll be here for the next 15 minutes to answer them.
For the EC member, because the I has 2 zero force members, would that I joint kind of like disappear? Would you kind of
Right here?
Yeah. Would you just kind of look for the member like you found one there?
The I joint?
Yeah.
Well, I mean, you can, because if you,
You're doing the zero force, like when you're doing the diagram, would you go from like AI or would you mark it AC, leaving the joint or entering the joint?
so I would do a joint here, figure out AI, and then I already know that, so I can do another joint right here.
So you just keep I in there.
Yeah. And for the surveys, if you haven't filled one up, please come up and get one and fill it out. Where I,
59 bubbled in.
no, I need 64. Yeah.
You need 64?
Yeah.
Oh, gosh.
No, you're fine. I know the one that was up there was a little misfilled, but anyways,
If it's okay if I did 59 then?
that's fine. Don't worry about it. Yeah, no worries. Yeah, I hope it was helpful, guys. I'll be here for the next 15 minutes again.
So, how did you know that
Thank you.
IG was a zero force center? Like, now that I'm looking at it, I can see okay, BC and CD and AB and ED and IAG. How IG? Why IG? How do you know that?
Well, you know there's a reaction right here, but if you do the joint, it's a perpendicular member on joints with constant force.
Okay.
It takes a while, man.
Okay. I mean, is it perpendicular? Or is it?
Yeah, it's supposed to be perpendicular.
Okay. Okay, because if it's perpendicular, I can
Yeah.
get that, but
It's supposed to
it
be.
just doesn't quite. I guess maybe it's just my eyes.
No, they made it that way so that you only have a distances on the bottom, right? And then you have some of the distances on top. But yeah, it's a perpendicular member.
Okay. So then are IG and GJ, are they perpendicular?
IG. So we were just talking about IG, right?
Yeah, IG and GJ, are they perpendicular?
And
also?
GJ. Yeah, I mean, it's symmetric,
Okay.
right? So unless there's an additional load on the outside, these are going to be equal, which there is. So that's why these aren't zero force members.
Okay.
Cool.
All right, thank you.
Yep. All right, I appreciate it. Thank you.
I have a question for you. I was working on our problem yesterday, and it was like a part, like a sphere, like part of
I
the sphere.
know that one, man.
Yeah.
Hey,
How do you do that? I was struggling hard.
so like the way I usually approach it is I take the entire sphere, and then I start quartering it.
Okay, but that doesn't quarter the volume.
No, it doesn't quarter the volume, but if you realize what happens to the, so this is actually, if you look this up, you'll have a quarter sphere. So there's an actual, with the moments of inertia, you'll see a center mass for a quarter sphere. And then you can see where it falls on there, and then you just kind of
You
end it.
can't make this 2D by any way? Or is that
It's been a while since I worked that problem. I can't remember how I did it originally.
that's dangerous grounds, probably.
I like making stuff 2D, so I'll do it a little bit longer and make it 2D to make a little more sense to me sometimes.
Because I try to make it 2D, and like we know what the centroid of like this whole thing would be,
Yeah.
but we wouldn't know what the centroid of that still.
Since it lies on the axis, you have the ability to make it 2D, yes.
Okay.
So you can, but you're just going to have to shift the equation around.
Okay.
Does that make sense?
Yeah.
Yep.
A little confused about the difference between the cumulative and the partial exam.
So I don't know what exactly is going to be on there. So the cumulative is going to cover the entire book, so you can test you on whatever.
How does that count in the grade? Like,
Oh, okay, so it won't hurt you. It can only help. So if it's better than your original test grade, it'll take the place of the old test grade.
that's the cumulative?
Yeah. If it's not better than your old test grade, it'll be a test by itself.
Okay.
That makes sense?
Mm-hmm.
All right.
All right.
Cool.
Thank you.
Yep. Thank you.